And we'll see now the other traversal method, which is breadth first traversal method, and the other types of tree. Okay, the special type of tree, which is binary search tree. Okay, but before going to that, we can now have different functions. If we have the tree created with us, we can traverse it. Then we can do different functionalities on that tree. Okay, different various functionalities, so we will discuss those other functions also associated with the tree. Okay, so most of you might have get the question, we are traversing the tree from left to right, and why not from right to left? So why only three traversal methods are commonly used? Okay, but we can traverse the tree from right as well. So right, root, left, that is also possible, and that will generate the in order, another in order traversal, pre-order traversal, or post-order traversal, where right subtree will be visited before left subtree. Okay, but these will generate only the mirror images of whatever tree we are creating. Okay, so uh, see, DLR, T is nothing but a current node. This is left subtree, this is right subtree. So this is general pre-order. This DLR is same as DRL. Okay, so they are the mirror images of each other. So any one can be considered. So most commonly we do the traversal using left subtree, root, and then right. Okay, but we can do reverse of that as well. The other three are also possible, but they will generate the mirror image of the current traversal which we have created. Okay, that's why only one of them can be used. These traversals are type of depth first traversal. As we saw, these traversal in order, pre-order, post-order, they are the subtypes of depth first traversal of the tree. And we use stack, either implicit stack or explicit stack, depending on whether it is recursive traversal which we are using or non-recursive. In non-recursive, we use our own stack object. Okay. Okay, so other subtype is breadth first traversal, where instead of using stack, because see, in depth first we are moving to the depth. Okay, in order traversal also we are moving to the leftmost of the node, and then we start traversing it. We pop and come to the parent, move to the right subtree, like that we continue. Okay, but in breadth first traversal we will visit the tree level wise. Okay, I will visit this level first, level 0 nodes first, then level 1 nodes, then level 2 nodes, all the nodes of level 2, then level 3 nodes, like that. Okay, so this is also called as level wise display of the tree. Breadth first traversal is also called as level wise display of the tree, where we start with root and we go far from the root. In every step we move to uh, one step ahead from the root. Okay, here we have one edge in between, then in the next level we have two edges in between, like that. So for doing the breadth first traversal, stack is not the useful data structure. Okay. Stack is not useful for breadth first traversal, because stack can be used for reverse accessing, but I don't want to access these nodes in the reverse order. Okay, but what I will do is I will use here, instead of stack, the queue data structure. And how queue will be useful? See here, I will check, I will start with H, okay, and I will move this H into Q, but H is the only node in this level, so I will dequeue it, and Q is the first in first out data structure, so H, which is moved first into the queue, that will be removed first from the queue. Okay, so H will be removed. After removing, we can enqueue its children nodes into the queue. Okay, so its left child is D and right child is L. Both will be enqueued into the queue. So in the queue we have D and L. Okay, then we will dequeue the next element, which is D, and enqueue its children nodes, which is B and F. Okay, but L is already there in the queue, so B and F will be inserted after L. Okay, then L will be dequeued, its children nodes will be enqueued into the queue. Like this algorithm will work. Okay, so algorithm for level wise display or breadth first traversal is: insert the root into the queue. Okay, we start with enqueuing the root node into the queue, and then while queue is not empty, do the following: delete a node from the queue and display it. So after dequeuing, we are displaying it. Remember that the sequence of enqueuing and dequeuing is same. So someone can display the node and then enqueue, that is also fine, because both the sequences are same. Okay, but fix your logic whether before enqueuing you are going to display or after dequeuing you are going to display it. Okay, both the logics are fine. So insert the node into the root node into the queue, then dequeue that node and display it, and then enqueue its left and right children. So insert a node corresponding to its left subtree into the queue, and insert a node corresponding to its right subtree into the queue. Then again dequeue and enqueue its children nodes, left child and then right child. This will continue until we come to the end. Okay, this is the algorithm. We will see the example of it, and then we will go ahead. Yes. Just a minute. We can see the example. This example, how our queue is enhancing along with. Why there is only 38 students in the class? Is any particular reason? Students are still joining. See, I'm not going to explain these algorithms again during the lab. You have to do it by your own, and you have to implement all these algorithms. Okay, I'll share the screen for the example. We have to do the level wise traversal, and we have allocated we have designed a queue class for this purpose. Okay, which will be used for the traversal. Okay, the nodes will be now waiting in the queue instead of stack. They will be waiting now in the queue, and in queue we know that the node which is entered first, that will be removed first. Okay, it follows FIFO. So the same sequence of nodes will be obtained after dequeuing, which is for enqueuing. Okay, this is the queue object. Suppose queue which is used for storing the nodes, and this queue is of nodes. Like we used stack of nodes in the in order, pre-order, post-order, non-recursive traversals. Similarly, this is for storing the nodes. Okay, and we'll start enqueuing H into this. Okay, we will start enqueuing the root. Root is enqueued. Okay, and that is the single node on the first level, level 0. So that will be dequeued. After dequeuing, we are displaying it. Okay, after dequeuing, we are displaying it, this. So this is the output. H is displayed. It is dequeued and displayed, and its children nodes are enqueued. And enqueuing sequence is left child is enqueued first, and then right child. D and L are enqueued. Then D and L are enqueued. Then again do the DQ. So DQ and display. So D will be DQ'd, it will be displayed in the output, and its children nodes D left and D right, that will be enqueued. D is D left and F is D right. Both will be enqueued. Okay. Again DQ, L will be DQ'd, it will be displayed. Okay. L will be DQ'd, it will be displayed, and enqueue its children nodes. So its children nodes are J and N. Okay, those will be enqueued. DQ, A will be DQ'd, will be displayed, and its children nodes will be enqueued, which are A and A. The next node F, it will be DQ'd, it will be displayed, its children nodes will be enqueued, which are E and G. E and G, they will be enqueued. Okay. Then so the next node is increase the size of the queue. So we have to predict proper size of the queue which can occupy all the nodes. Okay. So after B, F is displayed, is dequeued and displayed, and then its children nodes E and G, they are enqueued like this. Then dequeue, J is dequeued, it is displayed, and its children nodes I and K, they will enqueue. I and K will be enqueued. Then DQ will again happen. J is DQ'd, will get displayed. J is already, its children nodes are also enqueued. Then N is a DQ'd, N will be DQ'd, it will get displayed, and its children nodes M and O will be enqueued. M and O will get enqueued. Okay. This is our current queue. Now DQ, A will be DQ'd, it will get displayed, but its left and right children are null. So those will not be enqueued. Then again next node C, it will be DQ'd, it will get displayed, but its left right children are null, so they will not get enqueued. Non null children only are enqueued. Okay. Is dequeued, then it is displayed. After C, E will be dequeued, it will get displayed. Then G, I. So in whatever sequence they are enqueued, all will be dequeued because they are not having any children node. If any one of them is having left or right child, that would have been enqueued again into the queue. Okay. So this will be the sequence of displaying after dequeuing all these children nodes. Are you getting how queue is used for displaying the our tree in the level wise order? Is the algorithm clear?
Yes, ma'am.
Okay. So we'll go through the algorithm again. Insert the root node into queue while the queue is not empty. Delete a node from queue, display it, and insert its left child into the queue. Insert its right child into the queue. Okay. And if you want to see the code of it, then void level wise. We are having now the queue object. You have to write the queue class. As I told you in the practice assignment, you have to implement queue class using array. Okay, and use the object of that class. That queue should be for nodes. Okay, that queue should be for nodes. So just modify it for the node data and use the object of that queue. This we can use two objects as well as single object. So this is the algorithm which we saw now. Okay, single queue object. We start from root. So T, that is current node, it is root. If T is not null, NQT. Okay, so we have enqueued root. While not q dot empty, until the queue becomes empty, we are dequeuing from the queue. T equal to q dot dequeue. Okay, so current node is now the node which is dequeued. We are displaying it, that is visiting it after dequeuing. Dequeue, then visit, and then move to left. If T left is not null, enqueue T left. If T right is not null, enqueue T right. So its left and right children will be enqueued. Okay. Again dequeue, display, enqueue its left child, enqueue its right child. Okay. Like this, it will continue until the queue becomes empty, and that will give us the level wise display of it. Okay. Clear? So this is the algorithm which we saw, and there is one more algorithm possible with two queue objects. Okay, so we can use two queue objects, q1, q2, for doing the same thing, and q1 will be initialized. Initialization is nothing but making front rear equal to -1. Okay, so we are initializing the queue with front rear equal to -1. q1 dot nqt. So root will be enqueued in the first queue, q1, and while q1 is not empty, we are initializing the q2. q1 will be the queue with which is holding the parent nodes, and q2 will hold the children nodes, that is like next level nodes. Okay, so q2 will be initialized for the node which is currently uh, dequeued. Okay, so q2 will be first initialized, and then we are what we are doing is we are dequeuing from first queue and displaying. Dequeue from first queue, display it, and enqueue the children nodes into the second queue, q2 here. So children nodes we are holding in another queue. Okay, and before we begin the next iteration, we will call the second queue as q1, and we will generate another queue object for q2 for the its children nodes. Okay, that means what will happen for this tree, if I want to use two queue objects, this will be my q1, h will be in q1, and DL will be stored in Q2. And when becomes empty, I will ask this Q2 to become Q1, and Q2 will be created again for storing its children nodes. That is this next level nodes B, F, J, N. They will be stored in Q2. So this will be Q1 now, and this will be Q2. When Q1 will become empty, I will call this as Q1, and these nodes will be stored in the Q2. Okay, like that. So same thing we can do using two queue objects. So whichever algorithm you feel comfortable, you can use that. Okay. Is the level wise display clear? Using queue, how we have to do it? Shall we go ahead? Try to use these algorithms, use these functions, write these functions one by one into your tree which is created. Okay. Our second assignment is binary search tree. In that we have to write all these functions. So before we create the binary search tree, you can try these functions, all these algorithms on the first assignment as well. In expression tree also you can check the level wise display of that particular tree. Okay. For any tree you can try these algorithms. Shall we go ahead to the next functions? Is level wise display clear? Okay, thank you, Mrudul. Yes, we'll go ahead. Okay, so we have seen different methods for tree creation and also the traversal methods, different traversal methods. Then we can go on adding different functions into our tree program. If we want to display only leaf nodes, okay, we now know the traversal methods. Okay, we now know the in order, pre-order, post-order traversal methods, all those algorithms. So yes, you have these functions with you now for traversal. If you apply a condition for this printf, that is while visiting, if you check whether this T is leaf or not, T is the current node which you are visiting. You can check whether it is a leaf node or not by just adding one condition here. If T left is null and T right is null, that means it is a leaf node. So if we add here a condition like if T left equal to null and T right is equal to null, then only display the data. That will display only the leaf nodes, that is external nodes. Isn't it? Is it clear? If I add a one condition here, that will visit each and every node. We will go to each and every node, but we will display only those which satisfy this condition. Okay? For that only we are displaying the data. Or if I want to display all the internal nodes, okay, I don't want to display the leaf nodes. Other than that, I want to display all the nodes. So I will write the condition if this condition is false. Okay, that is both of these are not null, then only display the data. That means it can have one child or it will have two children, then only display the data. So I can have the reverse of it. I will say not here. Before this condition, I will say not. Okay. So like that, you can do various things now. If I want to count how many leaf nodes are there, I will have a counter initialized to 0 and we can increment those counter. That counter will be incremented only if this condition is satisfied. That also we can do. Okay, so that will have the count of leaf nodes. If I want to search a particular node, I will take a key from the user and I will pass here. I will pass the key as well. Okay, in our expression tree, that will be a character key. If it is the tree of integers, we can have it integer key. Or if it is tree of suppose student data, I can take the roll number and search accordingly. Like that, it can happen. So I will pass the key also along with the root node, and I will compare that key with t data here where I'm visiting. I will add the condition to compare the key. So if t data, it is same as the key which I'm searching for. Okay, then only display data, or then I can display if it is the student record. Okay, then I can display all the other information of that particular student. If roll number is matched, I can display the other information of that student. Or I can say that yes, the data is found, required data is found. Okay, like that, we can add a search function also in our tree. And which type of searching it is? It is the search. We cannot say here linear search. It is actually the sequential search only, where we are visiting each and every node and comparing the data which we want. Okay, and complexity of this searching function is big O of n, because we are visiting each and every node and checking whether it is the same data required. Okay, and not only in order, we can do that in pre-order also. Here where we are visiting the t data, we can apply the conditions for it. Okay, and write our search function, or we can display the leaf nodes using pre-order traversal as well, or post-order traversal as well. Use any of these methods to write your uh, recursive function for displaying leaf nodes or for searching a particular key. Even that you can do with the non-recursive traversal methods as well. Wherever you are visiting that node, that is the point where you can add different conditions of searching or of checking what type of node you want. Okay, all the non-recursive traversal methods also can be used for that. Are you getting? So you can write now the different functions. We have seen level-wise display algorithm. Then you can write search function. You can write the function to display the leaf nodes. Okay, so we have to add this condition in our traversals. Okay, and non-recursively also or iteratively also we can do that thing only wherever we are visiting the node using non-recursive in order, pre-order, or post-order traversal. Select any of the method and add this condition wherever you are doing cout. Okay. Then the next function is finding the height of the tree. Okay. Finding the height of the tree. So recursively also we can find the height of the tree. Yeah. So if the node is null node, we will return -1 for it. Okay, height of that null node is -1. Leaf nodes will be considered at height 0. That is, height of leaf nodes is 0. And see, we'll discuss with example. Okay, suppose we have to find height of this tree. Okay, what is the height of the tree? It is maximum of left subtree height and right subtree height. Whichever is maximum, +1 will be height of this particular root node. Okay, height of the tree is nothing but height of this root node. Again, for calculating height of D, I need to calculate height of the left subtree and right subtree, whichever is maximum, plus 1 will be the height of D. Okay, similarly, height of L will be calculated by calculating height of the left subtree and right subtree. Okay, and height of these leaf nodes will be considered as 0. All these A, C, E, etc. They are leaf nodes, so their height is 0. And height of B will be maximum of height of A and C. Both are at 0. So B is having height 1. Similarly, F is having height 1. All these nodes are having height 1. D and L will have height 2. And H will be having height 3. Okay. We'll see some asymmetric tree. Yes. In this case, if I want to find the height of H, I, E, F, G, all these will be 0. Okay, so height of D will be 1. Height of B will be this height of D is 1 and height of E is 0. So height of B will be maximum of its children height, that is height of D will be considered plus 1. That is height of B will be 2. And height of C is 1. So height of A will be calculated based on maximum height of the children. So height of B will be considered here. That's why height of A will be 2 plus 1, that is 3. Okay, so its left subtree is having more height than right subtree. So that will be considered plus 1 will be the height of A. Is the idea clear? For finding the height, it is calculated in the reverse manner from leaf to root. Okay, so we'll see the function again. Recursive function for finding the height. Yes, so if T is null, return -1. If T left is null and T right is null, that is for leaf node, return 0. For all the other nodes, we will find recursively height of T left, that is left subtree, and height of right subtree. These are the two recursive calls of this same function, height recursive. Height of left and right subtree will be found and 1 will be added into it. And whatever is maximum out of these two, left subtree height and right subtree height, that will be considered, that will be enhanced by adding 1. Okay, and that will be returned. Clear? So recursively, you can divide this statement. This is the statement which is doing 2-3 things. We are calling height for left subtree. You can store it in another variable. Okay, suppose L. Then you can have R variable where you can store height of right subtree. Then you can call maximum of LR. It will be another instruction. Then you can return the maximum whatever you have found plus 1. Okay, so this same statement you can divide into 3-4 statements if you are getting confused with it. You can say int L is equal to height of left subtree. And similarly, you can height of the right subtree. Then we can have one more instruction to find maximum int M is equal to maximum of L and R. Okay, so it will have the maximum height of left and right subtree. Maximum of L and R. And then we are returning M plus 1. we are returning m plus 1. So we are doing all these four things from this thing, from this one instruction. Okay, so it is the combined statement of all these four instructions. Any doubt? Any doubt in this? Is the height recursive clear? We will see height non-recursive in the during the practicals. But I think you should try these recursive functions at least. And I have seen that many of you have not started with non-recursive algorithm development. If you do like this, you will not get the algorithms clear. You have to go with me. We have seen non-recursive algorithms in on last Monday or Tuesday's lecture. You should immediately implement that, otherwise you will not understand all these further algorithms. Okay, then we have copying a tree. We can copy a tree by simply copying the data, then left subtree and right subtree. So I can do that recursively. Okay. P is the copy of our tree, and we can copy the data into it, left subtree into it, and right subtree into it. For every node, if we do like that, we can generate the copy of our tree. Then we can also have the mirror function where left subtree is attached to right and right will be attached to left subtree. So in the reverse manner we are doing this. P left is equal to mirror recursive T right, and P right is equal to mirror recursive T left. So we are doing exactly the reverse thing like we are doing here in copy. In copy we are attaching left subtree to left and right subtree to right of the current node being created. But here in mirror we are doing it in reverse. Okay, so you have to try all these functions one by one. Then only the idea will be clear. Okay, and non-recursive also we can discuss it during the lab. But at least recursive you should start. Okay, is there any doubt up to now in the binary tree, expression tree, traversals, and all these simple functions like displaying the leaf, finding height, mirror? Okay, fine. So try all these functions with your tree which you have created, either binary tree or expression tree, whichever tree you have created. Try all these simple functions. The next concept is binary search tree, which we have to implement in our second lab assignment also. Now, why there is a subtype again for binary search tree? We have seen that binary tree is required or it is useful than any general tree. What are the advantages of simple binary tree over other general trees? Yes. Why we have seen binary tree in detail? What is the advantage of binary tree? We have seen certain advantages, two, three advantages, and that's why we studied binary tree in detail. Yes. Any tree can be converted into binary tree, correct. Method we have seen left child, right sibling method, which helps us to create any general tree into binary tree. And easy traversal methods, these in order, pre-order, post-order traversals are easier. Yes, that is also one advantage. What is the other advantage? We have seen certain formulae related to binary tree, where nodes is given, we can find minimum and maximum height of that particular binary tree. So we can predict the tree easily if number of nodes are given. Okay, that is the third advantage of binary tree. Then binary search tree is another special type of binary tree where certain condition is followed. Binary search tree, it provides excellent structure for searching a list. We have seen search function now for a simple binary tree. We have seen search function, how searching is done in simple binary tree. We visit each and every node and check what is the data at that node. Isn't it? Any of the traversal method will be used and we will be visiting that node. Isn't it? Any of the traversal method like in order, pre-order, post-order, recursive or non-recursive, or even level-wise display, that method also can be used for searching a particular node. So what we are doing in that, we are visiting each and every node and at, we are checking what is the data present at that node. Okay, so that is simple searching on any of the binary tree. But what is the disadvantage there? We have to visit each and every data, each and every node in the tree. Okay, and the complexity of this searching will be big of n. Yeah, but if the number of nodes in a real time, these trees are used for representing the database or representing uh, any hierarchical data. We have seen the different applications. So if I want to search anything, there will be thousands of nodes in the tree, and that will make my searching complex. So if in order to reduce the complexity of searching, we can go for this binary search tree. Name itself suggests that it is the tree which simplifies our searching. Binary search tree, they provide excellent structure for searching a list and at the same time for inserting and deleting data into the list. So this will simplify searching as well as insertion and deletion of the nodes into the tree. A binary tree T is called a binary search tree if each node has the property. So what is the property of binary search tree? The value of n is greater than every value in the left subtree of n. N is the root node of the current subtree. That root is having greater value than each node in the left subtree and has less value than each node in the right subtree. Subtree, all the greater nodes are present. And this property is true for each and every node in the tree. Okay. So this tells you what exactly is binary search tree. So if k is the value present at root node, all the values in the left subtree are lesser than the root node, and all the values in the right subtree are greater than root. And this property will be satisfied by each and every node in the tree. Okay. So examples of binary search tree, if 12 is the root, okay, here 5, 7 is in between 5 and 12, is present in the right subtree. 4 is lesser than 5, that's why it is in the left subtree. Okay, like this. So this is BST of numbers, this is BST for strings. This is root, greater string is present in the right subtree, all the lesser strings are present in the left subtree. And if you see here, this is also a BST. The left subtree is also a BST. In this case also, the left subtree is also BST. So if you see here 5 as a root of this BST, left BST, then 7 is greater than 5 and 4 is less than. Similarly, this is also a BST. Okay? So every subtree is also a BST. 16 21 greater value is present in the right, lesser value 13 is present in the left, and all these are greater than 12, all these are lesser than 12. Okay, this is BST. If you traverse BST in order, just check what you are getting. Traverse this BST in order way and check what you are getting. Yes. Traverse this BST in order. So we'll start with 2, then it's 4, 5, then right of 5 which is 7, then 12, then 13, 15, 21. So if you see, in order traversal of BST is the ascending order of all the elements present in the tree. Okay, in order traversal of BST will be always in the ascending order. Okay, in order traversal of BST produces a sequential list. This is also one of the property. And if we display this in the reverse order, that is right subtree, then node, and then left subtree, we will get the descending order of the elements. Okay, if we traverse the tree from right, then root, and then left, it will give us the descending sequence of the elements. Okay, then where is the least value present in the BST? The minimum value is present at the leftmost. Okay, 12. This is the minimum value present. So if someone asks you to find out the minimum value in the BST, display the minimum value, you just have to traverse to the leftmost, that is the minimum value. And maximum, that is present at the rightmost. Yes. Okay. So maximum value is always present at the rightmost. Is clear? Okay. So try creating the BST for this particular data. Try creating the BSTs and do the in-order traversal of that BST. Okay, this is the assignment given for the before the next lecture. I want all of you to come with the answers. You can take the snap of this screen and solve all these 4 examples on paper. PhD dependent on how we store notes. Yes, Rohit, try first with these examples and then we'll discuss in the next session. Okay, try creating the BSTs for the data given for these 4 examples. Okay, create 4 different BSTs and then we'll discuss your point.